any other questions on clarity as to what we're doing before we get going? We're all on the same page now, hopefully.
Wait, when you ask about what is the strongest intermolecular force, you mean the bond?
So, like, let's say, well, we're going to talk about intermolecular forces today. Ask me that again at the end so I can tell you.
Okay.
That way you guys know what I'm talking about when I start describing what to expect. Okay, any other questions? So everyone knows what we're doing on Thursday?
Crying.
Crying? Okay. Chapter 12 is on intermolecular forces. And when we're talking about intermolecular forces, we're talking about interactions between neighboring molecules. Up to this point, we've only talked about intramolecular forces. So we talk about what holds a specific compound together. So we've talked about molecular bonds, ionic bonds. That's what holds a compound together. Now we're looking at the interactions between, like, here's one molecule of carbon dioxide, here's another molecule of carbon dioxide. What are they doing? How are they interacting? So that's what Chapter 12 is looking at, those neighboring interactions. I don't have my first page of the outline. We're just going to fly through the whole outline today. Helps if I have my first page. Okay, so the first thing we're going to do is look at the different types of intermolecular forces, and I have a couple ways I want to do this. The first thing that we're going to do is just kind of walk through the way that the textbook does it, and I'll just show you the pictures that are in the textbook to make sure that we understand what they're talking about. And then the second thing I'm going to do is I found actually a really cool simulation that basically sums up Chapter 12 in this really neat simulation. That you can actually see the electron clouds moving around. Is that on red or green? Red. Red.
Around this.
Okay, so the first type of intermolecular force that we're looking at is the dispersion force. Dispersion forces are the weakest types of forces. These are known as London forces, or also you can see van der Waals forces. Those are some different names for them. And every single molecule has a dispersion force. It doesn't matter if it's molecular, if it's a polar or nonpolar, ionic, whatever it is. There are going to be dispersion forces between neighboring molecules. And dispersion force is basically what causes them is the mobility of the electron cloud. So, for example, here we have helium. Helium, you have 2 electrons in helium. Those 2 electrons are not stagnant. They don't just stay in the same place. They're constantly moving around. And what this does is it shifts where the charge of that molecule is. So you'll have the 2 electrons moving around. And every once in a while, you'll get it where those 2 electrons are on the same side of the molecule. When this happens, that makes this side of the molecule over here have a partial negative charge, making this side have a partial positive charge. When neighboring molecules like that get together, what you see is they actually line up. So you have this negative here and this partial positive here. That will line up with a partial negative from an adjoining atom. So you end up with what's called these dispersion forces. They're very weak attractions. They're about 5% of the strength of irregular bonds. So they're very weak attractions, but this is what gives different substances their properties. So these intermolecular forces, they're responsible for things like the boiling points, for how volatile something is. It gives them their characteristic properties. When you have dispersion forces, these are very weak forces. They're not going to make something like an incredibly high boiling point molecule. You're talking about things with very low boiling points. They're going to vaporize pretty easily. They're a weak attraction, but they are an attraction. These are there. So you do need to recognize these. Whenever you see a nonpolar molecule, it is important to recognize that even though it is nonpolar, these dispersion forces do occur. So you still have those weak attractions in them. Nonpolar molecules do have these. Every molecule has them. So dispersion forces are in everything. Okay, so in your outline, I ask you, what factors affect the magnitude of dispersion force? So what affects how strong that dispersion force is going to be? I know I just jumped into your outline. Sorry. Second page. I know what I'm talking about. I know. Sorry.
The size of
the size of the molecule. What does the size of the molecule have to do with the strength of the dispersion force? So if you have a really big molecule, what does that tell you about the electron cloud? So a really big molecule, those electrons on the far outside, are they going to be very much attracted to the protons in the nucleus?
No,
there's very little influence, right? So do you think those electrons are going to move around easily, or is it going to be hard for them to move around?
Easily.
Very easily. So the bigger the atom, the more easily that electron cloud is distorted. So as you get to the bigger atoms, that electron cloud is distorted a lot more easily. That's going to affect how easily it can polarize, which affects the dispersion forces. So larger atoms will have a larger force because they can polarize more easily. So how does the strength of a dispersion force and the boiling point, how are those two things typically related?
The strength of the dispersion?
Yeah, so if you have a very strong force, if you have a high dispersion force, what do you think that's going to do to the boiling point? It's going to increase it, right. So the stronger the dispersion force, the higher the boiling point. So those two things are correlated. This is really important because one of the things you might be asked to do is to predict the boiling point of something. So I might throw out a nonpolar molecule and a polar molecule and say which one's going to have the higher boiling point. And you should be able to predict this based upon your knowledge. Or I might say, like, you have helium and you have xenon. Which one of those is going to have a higher boiling point? So helium and xenon, which one do you think is going to have the higher boiling point?
Xenon.
Xenon. And why do we know that?
Because it's large.
It's larger molecule, has larger dispersion forces. So you can use your knowledge to predict boiling points on these. So also, that, like I said, that correlates. If you increase the force, you increase the boiling point. Also, if you have an increased size of the atom, you have a higher boiling point as well. So those two go together. Okay, questions on dispersion forces. The next one is what's called a dipole-dipole. And the dipole-dipole, here's the smaller masses, that's in the text sheet. Dipole-dipole occurs between two polar molecules. So remember when we're looking at polar molecules, we have an uneven charge distribution. So here we have, this is, what is that, it's methanol. And what you have here is your oxygen up here, it's more electronegative, so it's a partial negative charge up here. Carbon's down here, this is our least electronegative of the oxygen and carbon. So this is our partial positive. We have this charge distribution. This is our polar molecule. In a polar molecule, if you line these up, you're going to get the positive from one of them to line up next to the negative for another one. These dipoles do not fluctuate like the dispersion forces. These are permanent. So you're going to have this continually occurring. They're not going to go away, come back, and go away and come back. They stay put. So it's a stronger force than the dispersion forces. So when you get the neighboring, like I said, you have the positive from one lining up with the negative for another one. What type of molecules, once again, will have dipole-dipole? I just told you. This is important. Polar. This is why VSEPR is so important. If I throw out a molecule at you, you need to know how to make something to understand if it is polar or nonpolar. You have to draw the picture and say, oh, this is polar, or oh, this is nonpolar. That is why VSEPR was so important, and that's why I'm hitting it again on Thursday. Okay, so when you look at a dipole-dipole, is this a stronger or a weaker interaction than dispersion? Stronger. So what do you think happens to the boiling point when compared to the dispersion?
It's higher.
Higher. So if you have two things with similar weights, the dipole-dipole is going to be stronger. It's going to have a higher boiling point than the dispersion forces. So this is a stronger force. Okay, so let's see here. All right, it talks about miscibility in your text at this point. What is miscibility?
Is it the
It was hidden in there. There's like a little paragraph thrown in there. That's why I put it in the outline.
Is it like oil and liquid?
Yeah, it's the ability to mix. I don't know why they chose that point to threw it in there, but it did. I think we've kind of talked about this a little bit, but we'll hit this harder actually, we've talked about this, I think. It's basically the like dissolves like, where you have polar substance dissolving polar substances, nonpolar with nonpolar. When you mix a nonpolar substance with a polar substance, that's the whole oil and water thing. They can't mix. You get those two separate layers. So that means it's immiscible. If it mixes, it's immiscible. So there's our nice oil spills. Those are always nice examples of immiscible substances. Okay, the next type of force. Why is it going there? We're jumping around in this slide. Okay. The next type of force is what's called hydrogen bonding. This is basically an example of a dipole-dipole, but it's what we call a super dipole. And it's a really, really strong dipole bond. Now remember, these still aren't as strong as like the intermolecular forces as an ionic or a covalent bond, but it is a very strong form of a dipole bond. Hopefully you were able to draw some interactions in a glass of water. When you draw this, what are the things that are interacting? So you have your glass of water. What makes up water? What is the formula for water? HOH, right? So what are the hydrogens going to interact with?
The oxygen.
The oxygens, right, of a neighboring molecule, and the oxygens interact with what?
Hydrogen.
The hydrogen. So here's kind of my picture of this. We have our hydrogen here. This is one water molecule. It's interacting with, we have our oxygen interacting with the hydrogen of a neighboring molecule. And then you have your HOH from that one. That hydrogen over here is interacting with another oxygen molecule. Something like this is how the interactions occur. Now, with this exam, I'll warn you, a lot of times I do ask questions like this. So this is something that a concept you should be able to visualize. So there are some interactions between those neighboring molecules. They orient themselves so that the positives of one molecule line up to the negative of the other, and the negatives all line up to the positive. Hydrogen bonds, there's only a few types of molecules that will have hydrogen bonds. What are they? They have to have one of three elements in them.
Nitrogen, oxygen, or fluorine.
Nitrogen, fluorine, or oxygen. If they don't have one of those, there are no hydrogen bonds. And if they do have one of those, they have to be attached to a hydrogen. So you can't have like N2 and say, oh, that's hydrogen bonding, there's nitrogen. It has to be attached to a hydrogen. So it has to be somehow, like NH3, that would be hydrogen bonding because there's N's attached directly to a hydrogen. If they're not attached to the hydrogen directly, then there is no hydrogen bonding. Okay, any questions on that so far? All right, so if I give you an exam, and I give you a bunch of molecules, and I ask you to identify what the intermolecular force is. If I ask you, basically, what type of molecules have a dispersion force? Everything. So what do you think a safe answer to write down always is?
London.
A dispersion force, right? London, van der Waals, whatever you want to call it, that's a great bet to write down. If I give you a polar molecule, what types of interactions is it going to have? Dipole-dipole. And if I give you something like H with the H and N, an H or O, an H or F, what's that going to be? Hydrogen bonding. So all you have to do is look at the molecule, say, is it polar, is it nonpolar, does it have a nitrogen, oxygen, or hydrogen, or fluorine, sorry. That's what you're looking at here. When we look at the strength of these interactions, I had you write down a chart. I don't know why I took it off. And you were supposed to write down this chart, and then you're leaving some room here because there's a few extras that I'm adding on. Your dispersion, the relative strength is weak. Remember, it increases with increasing molar mass. This is present in everything, all atoms, all molecules. Then we had dipole-dipole, which was moderate, and it's present in polar molecules. And then our hydrogen bond is strong. It's hydrogen bound to oxygen, nitrogen, or fluorine. The next types of forces, I sent you to another website to go look at. We have what's called the dipole-induced dipole. And the dipole-induced dipole ones, what you have here is you have a polar molecule with a nonpolar molecule. And what will happen is that this polar molecule will actually induce a dipole into the nonpolar one. So here you see HF, and it's neighboring our chlorine molecule over here. Chlorine is typically nonpolar. But what happens is as this HF, where the fluorine has the partial negative charge, approaches chlorine, it's going to shift all the electrons away from it. So all the electrons shift over here to this other side. leaving this with a partial positive charge and leaving that side with a partial negative. So you now have an interaction here between the two of them. So you might be asked on an exam to predict what type of interactions exist between these two molecules. It doesn't always have to be two molecules of the same. If you see a polar thing pulled with a nonpolar thing, that's going to be this dipole, this induced dipole. So it's dipole, induced dipole. So for that one, like I said, watch out for a polar molecule plus a nonpolar one. Questions on that one? Okay, the next type of interaction that I gave you was ion dipole, and this is where you have an ion come in to either it's usually to a nonpolar molecule or to even a polar molecule, sorry, and this is going to be, ion comes in here, you have, in this case I gave you calcium chloride, I just drew that one out, you have your negative chlorine, it's going to come up to our HF, and you're going to have that negative ion right there will interact with that partial positive on the hydrogen right here. So if you see an ion thrown in there and you see a polar molecule, you know that you have an ion dipole. This one is a little bit stronger than some of the other ones. It's stronger than the H bond, so it's actually quite a bit stronger than them. It's still weaker than an intramolecular force, though. And for this one, you're going to see an ionic compound or ions reacting with a polar molecule. So if you see that, that's that ion dipole. Okay, so I'm going back over here because you were supposed to kind of fill this in to fill out the rest of those forces. So here we have our two other ones that I added on right here, our dipole, induced dipole. This is weak, but it is stronger than the dispersion. So this, in order of strength, kind of goes between the dispersion and the dipole-dipole. It goes up here. That's what that arrow is for. And this is always between a polar and a nonpolar molecule. Then we have our ion dipole. This is stronger than a hydrogen bond, so it's down here at the bottom. It's the ion plus a polar molecule. And then that website also had ionic ones given to you. These are the strongest, and they're anionic compounds. So that was just thrown in there. Any questions on this? I think didn't I scan these and put these up on Blackboard for you too, so you have them completed? I'm pretty sure.
Oh yeah, you said the outlines.
Yeah. So you can actually refer to these on Blackboard too. Okay, so when you rank these in order of strongest to weakest, we just said it, but let's go over it anyways. What is the weakest of them?
Dispersion.
Dispersion. And what types of molecules does that occur between?
All of them.
Nonpolar. So even if you had Cl2 and like Br2, two nonpolar things next to each other, that would still be dispersion forces acting between them. Then after dispersion, what is next?
Dipole.
Dipole-induced dipole. So dipole-induced dipole is next. What types of molecules does that occur between?
Polar and nonpolar.
Polar and nonpolar. Then we have what?
Just dipole.
I should be looking at your charts, by the way. They're in order. Dipole, right? And what types of molecules does that occur between?
All polar molecules.
Two polar ones. And then we have what?
Hydrogen.
Hydrogen bonding, which is between what types of molecules?
Hydrogen. NOF.
Anything that has an N, an O, or an F attached to a hydrogen, right? And then we have what? Ion dipole, which is between what?
Two ions and a polar molecule.
An ion and a polar molecule. So those are the intermolecular forces that you need to be aware of and know how to identify. So when you approach these problems on an exam, what do you think you're going to want to do? When I say identify the intermolecular force acting in here, what are you going to want to do? Figure out if they're polar or not, right? That is step one. So polarity is incredibly important on these. If you don't know how to determine if something's polar or not, you're going to fail. This is where everything starts catching up. So make sure that you review all that with Vesper, and we can get that going pretty well. Okay. The problems that I gave you here are very similar to what I usually ask on exams. So it says for each of these compounds, determine the main intermolecular force. So the main intermolecular force, do you think that means the strongest or the weakest? The strongest. So you're telling me the strongest intermolecular force on this. And pay attention, you may find it useful to draw Lewis structures for some of these molecules. So when we look at nitrogen, what is the formula for nitrogen? N2. Nitrogen is diatomic, right? It's one of those diatomic atoms we talked about a long time ago. So N2, do you think that's going to be polar or nonpolar?
Non-polar.
Nonpolar. It is symmetrical. So it is. You have two nitrogens pulling equally on those electrons. That is nonpolar. So what type of force is the strongest force possible?
Dispersion.
Dispersion. It is nonpolar. It can only be dispersion forces. Then we have carbon tetrachloride. What is carbon tetrachloride? See what?
CL4.
CCl4, if you draw it out, it looks something like that. Is that going to be polar or nonpolar?
Non-polar.
Nonpolar. It's symmetrical. There are no lone pairs. That is nonpolar. So what type of force can it have?
Dipolar-induced dipole?
It's nonpolar.
Oh.
So it's just dispersion.
Just dispersion, right? So only dispersion. Then we have H2S. What is H2S called?
Sulfur dihydride.
Yeah, dihydrogen sulfide.
It's an acid.
Oh.
Wait.
Not sulfuric, that's H2SO4.
H2.
If there's no oxyacid, you don't put that. You have to put something in front of the name. You put it's called hydrosulfuric acid. Yeah. Okay. So we have our H2S. We're going to hit acids and bases again here next week. So there's been this next week. No worries. All right. So is this polar or non-polar?
That is polar.
This is polar. How do we know it's polar?
It's bent.
It's bent. What else screams polar to you?
It's not symmetrical.
Lone pairs. There are lone pairs on that sulfur, right? Okay. So for this one, it is polar. Does this have hydrogen bonding?
It does not.
No.
It does not. Because what do you have to have for hydrogen bonding?
Fluorine, nitrogen,
F, N, or O. So it's polar, not hydrogen bonding. So what type of interaction does this have? Dipole-dipole. Okay, the next one we have sulfur monoxide.
SO2.
Okay, is this polar or non-polar?
Non-polar. Polar. Non-polar.
Why would it be non-polar?
There's no center lone pairs.
Are these two going to pull the same equally on the electrons?
I would say because there's.
Well, the oxygen is more electronegative.
Oh.
Okay, and how do we know oxygen is more electronegative?
Higher?
It's higher. So will these two pull equally on the electrons then?
No.
No. So what is this? Polar. So what type of interactions will it have? Dipole-dipole. Yeah. So this is, once again, using that knowledge that we've learned so far. Okay, into H2. Okay, for this one, is this going to be polar or non-polar? This one's kind of a tricky one.
Polar. Because of the lone pairs, they push.
Are the lone pairs on a central atom, though?
No.
No. Is there symmetry here?
Yes.
There is symmetry. So is this going to be polar or non-polar?
Non-polar.
This is non-polar. Yeah, there's a plane of symmetry right here. If you divide this, everything over here is going to pull equally to everything over here. So that one's a little tricky. There's not a central atom with the lone pairs. So this is non-polar. So what type of force does this have? Dispersion. Yeah, that's it. Yeah, this is not hydrogen bonding because it is not polar. So in order to have hydrogen bonding, you have to have a polar molecule. So I know, tricky. Okay, the next one, boron trihydride. Is this polar or non-polar?
It's non-polar. Or polar.
Okay, let's think back to our VSEPR. Is this going to be symmetrical?
No.
Is there a plane of symmetry? Because I think
No.
if I were to draw this more properly, it would look something like that, probably.
No.
Could I fold this in half?
Yes, and
But
this
not.
way, but not the other way.
Yeah.
I can fold it this way.
Oh.
I can't fold it that way, right? But remember, this is a molecule in 3 dimensions, right? So
Oh.
can I rotate
So
it?
yes.
But didn't you do that with the actual 3D and you couldn't flip it because it's like
That was when there was 4.
Oh.
There was 4 things there. This one is actually going to be nonpolar. I know this is where that 3-dimension stuff really messes with your mind. There are no lone pairs here. Most of the molecules that we see like this that we say, oh, it's polar, there's been lone pairs up here.
Mm-hmm.
There are no lone pairs on this one, so this is actually going to be nonpolar. So knowing that, what type of forces will it have?
dispersion.
Dispersion. Next one. Okay, we have CH4OH. Is this going to be a polar or a nonpolar molecule? Do you see symmetry in there?
No.
Carbon's our central atom. I don't. So what type of molecule will this be?
Polar.
Polar. Now, what type of bonding will this have? Right here allows for our hydrogen bonding. So we will have hydrogen bonding between the OH group here and then whatever the OH group on the neighboring molecule is as well. So you'll have a bunch of partial negative with a partial positive, and you're going to have them orient themselves and have hydrogen bonding occur. Then we have SiOH2O. This one's kind of a fun little Lewis structure. And there might be some different ways that you can draw this. So for this one, is this going to be polar or nonpolar? Polar. Yeah, there's no symmetry there. And what type of bonding can we have on this one? Hydrogen bonding. You have the O attached to the H again. Okay, continuing on. So another way of phrasing it, once again, we're looking still at intermolecular forces. We want to know which one's most important, so once again, the strongest. We have FCN. Looks like this. Is this going to be polar or nonpolar? This is polar, so what type of bonding? Dipole on this one. The next one is HCN. Looks remarkably similar. What are we going to have there? Dipole. How do we know dipole? Because it's polar as well. So this one's also polar. C2H6. For this one, is this polar or nonpolar? Nonpolar, so what type?
That dispersion.
Dispersion. And our second to last one, sorry. There's different ways that you can have drawn this, but remembering our 3-dimensional models, it doesn't really matter what you put where. Is this going to be polar or nonpolar? Thinking of back to when I did that chlorine thing in lab.
No.
Oh, yeah.
Wouldn't it be nonpolar?
Because
This
of chlorine?
It's polar. Yeah, remember when I did that where I replaced it and it didn't matter where I put it? Because in 2 dimensions, it looks like if I change them, all of a sudden we have something different. But when I did it on the molecule, it didn't matter. They all look the same. So this is polar, which tells us that we have what types of interactions here?
Dipole.
Dipole. Why is there not hydrogen bonding?
Because it's not.
So hydrogen is bonding
Because
to fluorine.
Yeah.
The H is attached to the carbon, right? It's not attached to that fluorine. So the only way to have that as hydrogen bonding is if the H was attached to the F, and it's not. So we don't have hydrogen bonding. Okay, and then the last one there, I have water. And then I have ethane, C2H6. Is water polar or nonpolar?
Polar.
This is polar. And then C2H6 I just drew a few minutes ago. Was that polar or nonpolar?
It was nonpolar.
Nonpolar, right? So if I have a polar and a nonpolar molecule that are neighboring each other, what type of interaction are they going to have? Dipole-induced dipole. So this is the process that you're going to go through when you are taking a quiz, exam, whatever on these. It's kind of polar, non-polar, and then if it's polar, you have to go through the series of events to figure out what type of force it is. Any questions on those?
Is this for the quiz, not just the exam?
Yeah, this will be on the quiz too. So this is what I was talking about, like what you'll see on that VSEPR is, you have to draw the Lewis structure, then you have the VSEPR shape, whatever the shape is, and then I'll probably say something like the intermolecular force. And so I'll ask you maybe, I don't know, let's do HBr. I'll say HBr, draw the Lewis structure. Okay, HBr. VSEPR, it's linear, same thing, HBr. Get all the one pairs there. Probably ask if it's polar, and you'll say, yes, it's polar. And the intermolecular force there, if it's polar, what is that intermolecular force between stuff going to be? Dipole. So you just go on it.
Okay.
So be something like that. Okay, questions on that? All right. Continuing on then, let's look at these types of solids. Okay, so we're going to be looking at a couple of different types of solids. We're looking at the crystalline solids, what types we have, and we have three main types. We have molecular solids, we have ionic solids, and we have atomic solids. Molecular solids, when this pops up, there we go. The composite units for them are molecules. So in order to have molecules, what types of compounds are we looking at? Am I looking at ionic or covalent? Covalent. So for molecular compounds, you're looking for covalent compounds. So covalent tells us what? What types of atoms are we looking at?
Non-metal.
Non-metals, right? So multiple non-metals bound together. Things like carbon dioxide, molecular solid. These typically have very low melting point. We have ionic solids. What type of elements am I looking at there? For ionic, if it's an ionic compound, what does it have to have?
Metal, non-metal.
Metal and a non-metal, right. So we have our metal and our non-metal. So whenever you see like sodium chloride, something like that, that is an ionic solid. Same thing like if I said potassium phosphate, that's an ionic solid. So even if you have a polyatomic ion thrown in there, if you have that metal, you still have an ionic solid. And then we have our atomic solids. These are composite units, are just single atoms. With the solids, you can kind of predict the melting points of things if you know what type of solid it is, and that goes for the molecular and the ionic. Molecular, like I said, these typically have very low melting points. Ionic tend to have very high ones. Just think of trying to melt salt. It takes a high temperature to do that. With the atomic solids, you can't really predict that. So those depend on other factors, so we don't really say that you can use that as a prediction of them. Within atomic solids, we also have three different types of atomic solids. We have covalent atomic solids, and these are things that are held together by atomic bonds. So this is going to be that non-metal side again. Silicon is an example of one. If you had sulfur by itself, that's a covalent bond. So we would have covalent solids. These have pretty high melting points. Diamonds, carbon. Think of it that way too. Non-bonding ones, these are held together by dispersion forces. These have low melting points. These are going to be your noble gases for the most part. So things like xenon, argon, those are all going to be your non-bonding ones. And then we have metallic ones. These are held together by metallic bonds, and their melting points vary again. So your transition metals are usually going to be what pops up here for the metallic ones. So with these, what I expect you to be able to do is to identify it's like here for this problem, identifying whether something is a molecular, ionic, or atomic crystal type structure. So if you see CO2, excuse me, what is CO2 going to be?
Yeah. Non-bonding.
Remember, this is just for the atomic ones. We also have ionic and covalent. So we had the molecular, we had the ionic, and we had the atomic. So of those three, molecular, ionic, or atomic, which one is it going to be? Molecular. So we had a molecular for CO2. What does that tell you about its melting point?
Low.
Very low. In fact, it's sublime. It's just, it doesn't even really melt. It goes straight to the gas phase. If we look at nickel, nickel is what it is, molecular, ionic, or atomic?
Atomic.
Atomic. How do we know it's atomic?
It's a transition metal.
It's by itself, right? It's all by itself. There is nothing bound to it.
Wait, so anything that's not bound to something is
It's going to be atomic.
Atomic, right?
Mhm.
Yeah.
So of the three atomic types, which one is it? Is it going to be the covalent, the non-bonding, or the metallic?
Metallic.
Metallic, yeah. Okay, then we have I2. What is I2 going to be?
Non-bonding.
Atomic. No.
Now,
Molecular.
I2, is that by itself or is
No.
that a compound?
It's a compound.
That is a compound.
Molecular.
So what is it going to be then? Molecular. Yeah, that's molecular.
If it was I by itself, would it have been
It doesn't exist that way, but yeah.
technically it would be.
Those diatomics, they're molecules, so they'd be considered molecular. Okay, then we have CaCl2. What is CaCl2? What's that called? Calcium chloride. So what is calcium chloride?
Ionic.
Ionic. And how do I know it's ionic?
Non-metal metal.
Metal and a non-metal. So those are the kind of the clues to look for there. Okay. Then the book goes on to talk about water really quickly. Ways in which water is unique. We'll just talk about this really briefly. High boiling point, liquid at room temperature, even though it is a very low molar mass. Everything else that's around its molar mass is gas at room temperature. It's highly polar, and it expands when freezing. Those are just some of the ways in which it is unique. Okay, questions so far? All right, let's jump back to the beginning then. So the very beginning of this talks about some different properties of solutions, and it helps to understand the intermolecular forces before we go to talk about this, because now you'll understand why these properties exist. So the difference between solids and liquids and gases, we've already talked about this way back in like chapter 2 or 3. Gases, remember that they have indefinite shape, indefinite volume. They have very weak intermolecular forces. So things that have dispersion forces are typically going to be gas. If they're only dispersion forces, they will usually be gas at room temperature. Liquids, indefinite shape, definite volume, moderate strength of intermolecular force. So if it's a liquid at room temperature, you're usually looking at something like a dipole-dipole or a dipole-induced, ion dipole, one of those type things. Hydrogen bonding, a lot of times, is also going to be something that is a liquid at room temperature. Solids, these are things with very strong intermolecular forces. So in this case, we have sugar. This is an example of a molecular solid, a molecular crystal. These have higher intermolecular forces. Ionic compounds typically are solid at room temperature, very strong intermolecular forces there. Okay, so we're going to jump straight into surface tension. What is surface tension?
The molecules of the surface of a liquid, they don't interact as much with the more central one, so they create tension, and you can kind of penetrate it, I guess.
They like minimize the surface area.
Yeah. So
Why do they want to minimize the surface area? What is the point?
What do they want to?
Yeah. So they want to minimize this top, how many things are exposed to the very top layer. Why do they want to do that? It's up on the screen. Deduce from that information, why do they want to be deeper down?
To interact more?
They have more interactions. If they're at the surface, you see, like in this example, they only interact with 4 neighbors. Down here in the middle, they interact with 6. So what they do is they minimize the surface because these interactions stabilize them. So it wants to be more in the middle. So you minimize that surface, so the surface area is actually minimized. It's smaller when you have something with a high surface tension. Now, what do you think is going to have a stronger surface tension? Something with higher intermolecular forces or something with lower intermolecular forces? Higher. Why do you think higher?
They're attracting each other.
They're attracting it stronger, right? So is something like a dispersion force or a dipole-dipole going to have a higher surface tension? Dipole-dipole. So you look at a polar molecule, you know it has a higher surface tension than a nonpolar molecule. Put this to practical use. Let's think about gasoline. What is gasoline? Is it polar or nonpolar? Nonpolar, right? Versus water. What's water?
Polar.
Which one of those can you float a paperclip on?
Water.
Water. Have you ever, well, I've never tried this, but have you ever tried to float a paperclip on gasoline?
chemistry teacher
It's
didn't
not
have
going to work. So you can see those, if just by your knowledge of what gasoline's like, you should be able to see that. I don't recommend going home and trying that and making yourself sick with the fumes. Okay, so the intermolecular forces, what types of compounds will have the stronger intermolecular forces? What did we just say? In order to be dipole-dipole, what type of molecule is it? Polar. So things that are polar, things that are ionic as well. Okay, so there's our paperclip. Okay, the next topic was viscosity. What is viscosity? How thick something is. That's one way of looking at it. What else?
How slow, tension in between the intermolecular.
How slow it flows, the tension. So it's the resistance to flow. Yeah, so it's the resistance to motion. So obviously you have maple syrup. Is maple syrup what you would consider a viscous material or a not viscous material?
Viscous.
It's very viscous, right? It has a lot of resistance to flow, especially the good kind. Okay, so we have resistance to flow there. What types of forces do you think are going to give you a more viscous material? Do you think weak ones or strong ones?
Strong.
Strong ones. Why do you think strong ones?
The molecules are more tightly
Let's think of back to when we talked about solids and liquids. When we talk about the difference between solids and liquids, we're looking at the strength of those bonds, right? When you have an ionic compound, you're typically solid at room temperature. Why? What can those molecules not do? Move, right? So there's no movement. So if I have two neighboring molecules that have a strong interaction between them, are they going to be able to flexibly move around?
No.
No. So the stronger those interactions are, the less easily they can move around. So the stronger the intermolecular force, the less free motion you have, so the more viscous you have. Also, and along with this, you also have some things that you'll notice are nonpolar, but they're quite viscous. How does that work? How can you have something that's nonpolar but also be viscous?
The
This was
bond.
in your book. Yes. Entanglement. Yes. What do you think entanglement means?
It creates a
The
net.
molecule.
The
Yeah.
molecule
There's a
tangle.
net. What size of molecules do you think you have to have for that?
They're long.
Really
Yeah,
long.
like hydrocarbon.
So, like, if you have a really long hydrocarbon, let's think of, I don't know, let's see here.
I think it talks about motor oil.
Yeah, kind of like motor oil.
Oh, yeah, because
When you pull it in there, yeah, like a long hydrocarbon chain. If you think of motor oil, when you pour it in there, when that motor oil, like, how many of you guys have ever filled up the oil in your cars? Okay, good. Some of y'all need to open up that hood of your car and take a look under it sometime. When you pour that oil in there, is it like pouring alcohol? I'll just use that as the analogy.
No.
No, what is it? Is it thicker or thinner than it? It looks thicker. It's actually more viscous than if you were to say rubbing alcohol as a comparable material. And that is because it has a much longer hydrocarbon chain. I'm not actually sure what the formula for motor oil is. It's probably quite long. But it is a much larger molecule, so you get that entanglement in it. So you have to have something with either high intermolecular forces or something that's a really long hydrocarbon. So hydrocarbons, we're talking about things that are hydrogen and carbon only, so usually gases of some sort, fuels of some sort. Okay, questions on viscosity? Okay, so then I give you a series of terms to define. So let's just quickly go over these. Evaporation, what is it? You go from a liquid to a gas, right? If something is volatile, what does that mean? It evaporates easily. If it is non-volatile, what does that mean? It doesn't evaporate. Okay, so if something is volatile, it evaporates easily, what types of intermolecular forces do you think it has?
Dispersion.
Dispersion. Weak ones. It's going to have weak intermolecular forces. If it is non-volatile, what types will it have? Stronger ones. So things like our dipole-dipole or hydrogen bonding, things like that. Okay, then we have condensation. What's condensation?
Yes.
From a liquid to a
Gas to liquid. Dynamic equilibrium. What's that? Rate of condensation and evaporation are the same. So when you have like a glass of water sitting out on the counter, what's actually happening is that you don't have just evaporation occurring. There are times where the molecule collides back with the surface and it comes back into the liquid form. At dynamic equilibrium, what that means is that the number of molecules leaving the liquid is equal to the number of molecules entering the liquid at any time. So you have this equal switching around going on.
Is that when they measure boiling point? I wasn't really sure.
With vapor pressure.
Okay.
Yeah. So vapor pressure, what was vapor pressure?
The
partial pressure
of the vapor.
That's in dynamic equilibrium with the liquid. Yeah. So vapor pressure, what you're measuring is when dynamic equilibrium occurs, you're measuring the pressure that that vapor is exerting on the liquid. Boiling point is what? Boiling point?
Which the vapor pressure of the liquid is equal to the pressure above.
Right. So when that vapor pressure of the liquid equals the pressure above it, that's when you're going to have boiling. This is why things boil at different pressures, different temperatures. So at higher elevations, you have less pressure pushing down into that liquid, so it boils at a lower temperature. So that explains that science there. Normal boiling point, what is that?
100 degrees Celsius at a pressure of 1 atm.
There you go. Okay, so factors that affect vaporization. We've talked about if you have a volatile liquid, you have low intermolecular forces. So as you decrease the strength of the intermolecular forces, you're going to increase the rate of vaporization. What do you think happens as you increase the surface area? What's going to happen to the rate of vaporization? So you increase the surface area, you make more top, if you will. So like instead of having a little container, you have a big container. What happens to that rate of vaporization? Increases. So increase the surface area, increase the rate. If you increase the temperature, what happens?
It
increases the rate as well. So those are the big factors for that. And we talked about that. Okay, so vapor pressure. Vapor pressure is kind of one of those that you have to flip your mind around, because so far we've talked about, okay, if you have something with a strong intermolecular force, it's not going to vaporize very easily. So if you have a strong intermolecular force, that means that there's not much vapor up there. So what does that tell you about the vapor pressure?
It's low.
It's low. So if you have strong intermolecular forces, you're going to have low vapor pressures. If you have weak intermolecular forces, you're going to have very high vapor pressures. So CO2, for example, would have higher vapor pressure than water. So it's kind of, sometimes you have to put your head around that. Okay, so increased temperature, you increase the vapor pressure, obviously, because you're going to make more things go into that gas state. And then if you decrease the intermolecular force, you're going to increase the vapor pressure as well. Why is it vapor pressure independent of surface area?
Because like the higher the surface tension, like
If you change the surface area, you're also going to change the total number of things that are evaporating and condensing. So you're going to have the same rate of dynamic equilibrium. That's going to be the same. So the vapor pressure is completely independent of surface area. So that you're looking at the vapor pressure, remember, you're looking at the dynamic equilibrium. So how many things are going into the vapor state versus how many are coming back down into the condensation. That's not going to change as you increase that surface. Okay, let's see here. Any questions on that? All right. The next thing we're looking at then is boiling. Got my pages out of order. Sorry. So boiling. What happens when a substance is boiling? It bubbles. Okay, and what are those bubbles?
Thermal energy? Oh, wait, no.
They're pockets of gas. So like in the case of water, it's going to be pockets of gaseous water. So boiling occurs down at the bottom. You have down at the bottom here, you have this heat source, and you have water molecules getting hot enough to become a gas, and they go up to the surface and they go out to the steam phase. So boiling takes heat. It takes heat to boil. When these Okay, so when you have the boiling water, unfortunately we can't see this, but what happens is when the water boils, you have molecules down here that are gas. So here's your gases, and they're breaking through the surface and leaving. What is the energy of those molecules down there? Is that a high energy or a low energy substance right there? High. How do we know it's high?
Heated.
It's heated. It's in the gas phase, right? Do you think the energy of this bubble right here is greater than the energy of all the water molecules in the solution still?
Yeah.
Yes, it's much higher energy. When these leave, what happens is that energy leaves with them. So that energy goes out. That lowers the energy of the liquid that is left. This is an endothermic process. It's a little backwards to what you might actually think. So when that leaves the solution, you have an endothermic process. As this is condensed, when these gas molecules come back in, now you have something that's a high energy coming back into the liquid, and it adds energy into that liquid. So that is actually an exothermic process. So evaporation, endothermic, condensation, exothermic. So a little weird, but that's actually the way it works. When we're talking about vaporization, we have what we call heat of vaporization. What is the symbol for heat of vaporization?
Delta H.
Delta H, and then you usually put a little vape behind it like that. So for heat of vaporization, when we're talking about that, it's that delta H vape. And what is the heat of vaporization? Amount of heat required to vaporize 1 mole of a substance. So when you're doing calculations with these are numbers that are actually given to you. And, oops, I turned it off. You would find it in a table.
Do we memorize those, or?
No, you do not need to memorize these. These are numbers that are given to you. And they are not the same for every substance. So like you'll see here in this table, we have the heat of vaporization, and this is at both their boiling points and at 25 degrees Celsius. Heat of vaporization changes with temperature. So here we have, for example, water at the boiling point. At water's boiling point, its heat of vaporization is 40.7 kilojoules per mole. At 25 degrees Celsius, it's 44 kilojoules per mole. If the water's not as hot, it's going to take more energy to get it to actually go in the vapor phase. So that should make sense that those should be larger values over there. Isopropyl alcohol, you'll notice its vaporization is lower than water. Acetone, diethyl ether, they're up there as well. So the heat of vaporization changes based on the substance. They will be given to you. Okay, so do you think molecules with weak intermolecular forces will have a large or a small heat of vaporization? So it's like something that's nonpolar. Is it going to be a small or a large heat of vaporization?
Smaller.
Small. It's not going to take as much energy to vaporize it. So as intermolecular forces are weaker, it's going to be a lower heat of vaporization. Okay, so we have a couple problems here. Pretty simple calculations on this part. So we're wanting to know how much energy it will require to vaporize 43.2 grams of water at its boiling point. So for this one, all you have to do is really just convert grams to moles and then look up the heat of vaporization, and that's your simple calculation. So we take our grams, convert it to moles. How do I convert grams to moles?
You take the formula mass.
Molar mass, right? So it's approximately 18 grams of water per mole of water. And then, if I look at my heat of vaporization at the boiling point, what is the heat of vaporization of water at the boiling point?
40.7.
40.7. What do you notice about the units? What are they?
Kilojoules.
Kilojoules per mole. That's my conversion factor. So I just plug in 40.7 kilojoules per mole, run the calculation.
Do we indicate whether it's endothermic or exothermic?
If it's asked, you can. But I didn't ask on these. I typically don't ask that on these kinds. Usually, usually most of these are exothermic. Okay, questions on that one? Does that make sense where I got the number, that kilojoules per mole number from? Everyone see where that came from, hopefully? Okay, the next question is what quantity of acetone may be vaporized if 542.6 kilojoules of energy is put into the solution at 25 degrees Celsius? Same concept here, we're just kind of working backwards. So for this one, we start with our given, which is at 542.6 kilojoules. And I'm going to figure out how much acetone from that information. So to figure this out, I once again have to go to my chart and figure out what my heat of vaporization is. Now with this, notice that it says at 25 degrees Celsius. So what is my heat of vaporization for acetone that I'm going to use?
31.0.
31.0. So I have to make sure I find the acetone at that 25 degrees Celsius, not at the boiling point. That's the trickiest part. So for this one, my 30.1 is down at the bottom because I have 30.1 kilojoules per mole. So now I have my moles of acetone. For moles of acetone, I can go to grams of acetone. How do I do that?
Where did you go from kilojoules?
That's 31.
Yeah.
I think it should be 31.
Oh, 31. I'm sorry. I have it written down here as 31. I completely pushed it up here. I apologize. I have it right here. Okay, so I have 31 kilojoules per mole. Now I want to go from moles to grams. How do I do that? My molar mass, right? So I know 1 mole of acetone is, it looks like I wrote 58. About 58 grams. So 1,015 grams of acetone can actually be vaporized. Questions on that one? Okay, so this is our heat of vaporization. We also have something that's called the heat of fusion. Heat of fusion. What is going on for heat of fusion? What is occurring?
The amount of heat required to melt 1 mole of a solid.
So I'm melting a solid now. So now, instead of going from liquid to gas like I did there, now I'm going from a solid to a liquid. So heat of fusion is represented as delta H, and this time, instead of the H down the bottom, we put FUS, so it's going to be heat of fusion. Same thing with this one. If you have smaller molecular forces, you're going to have a small heat of fusion. So those are kind of it's the same thing. Weak intermolecular force makes it easy to melt. So let's go to the calculations for this. I just want to make sure I get through it. My nose is starting to throw me fits. Okay. So let's see here. The table for this one. There we go. So we want to know how much energy is required to freeze 15.8 grams of diethyl ether at negative 116.3 degrees Celsius. So my given here is at 15.8 grams. Before I can do any calculations, what do I need to do to this first? I need to go to moles with my molar mass, right? So I have 74 grams per mole. I look up the values in my chart. At negative 116.3, which is my melting point, what is my heat of fusion? 7.27 kilojoules per mole. So once again, our units kind of tell us what way to go. And in this case, you should have got about 1.55 kilojoules. Questions on that? Okay, the next one, we want to know what quantity of rubbing alcohol may be melted if 68.9 kilojoules of energy is pulled out of a solution at negative 89.5 degrees Celsius. So that negative 89.5 is its melting point. So I have 68.9 kilojoules, and I'm working backwards again. So to get from kilojoules to my mass, what am I going to have to do first? My heat of fusion, right? So I look at my table, I see my heat of fusion is 5.37 kilojoules per mole. So I write that as a conversion factor. That gives me my moles. Now I need to go from moles to grams.
1 mole
It's about 60 grams. So you should have been able to get the formula from there. So you should have ended up with approximately 770 grams of rubbing alcohol. Okay, questions on that? Does that make sense so far?
Yes.
Okay. All right, sublimation. There's a little section on sublimation. What did it say?
A solid goes straight to the gaseous state without going through the liquid state.
Right, so you go straight from solid to gas. There is no liquid state. What types of intermolecular forces do compounds usually have that sublime? What do you think?
Weak.
Huh?
Weak.
Very weak, yeah, very weak. You're not going to have an ionic compound that's sublime. That's just not going to happen. Okay. The last section there, I say putting it all together. This is a walkthrough on how to calculate how much energy it takes to convert something from a solid all the way up to a gas. And I give you kind a step-by-step section as to what you need to do. And the first thing I refer you to is, I don't think I'm going to get to my simulation today. Oh well.
Just do it.
I'll show you the link for it so you can go look at it on your own time. Because it is a very good walkthrough on intermolecular forces. Okay, so the first thing I refer you to is a diagram like this. This is what's called a phase diagram, and it shows the heat as you're going through the different phases. So here you'll see the phase diagram for, in this case, I think this is water. Yeah, that's water. And what they're showing you is the amount of heat that it takes to either change phases or to heat up the liquid. So this first phase over here, this is where you have a solid, because it's below its melting point, its freezing point. And this solid is being heated up from negative 25 degrees up to 0 degrees. All that is going on in this part right here is the solid is being heated. At this point, at 0 degrees Celsius, what's happening is you now have a phase change. This is where your heat of fusion comes in. So here you have all the heat going into this is melting. It's breaking some of those bonds so that there's more motion, and you get the solid going to the liquid. Over here, you now have everything as a liquid, and the liquid is now being heated up from 0 degrees all the way up to 100 degrees. So you have heating the liquid. Then when you get up to 100 degrees, right here, that is heating that liquid, so it's breaking all the intermolecular forces again, so we now can go into the gas phase. So this water is being converted into the gas right here. Once you hit this point, everything is now in the gas phase, and that gas is being heated up over 100 degrees Celsius. So these phase diagrams kind of give you a picture of what exactly is happening every step of the way. You need to understand these. I will draw phase diagrams a lot of times on a test and say, tell me what this says. Label all the points. So understand these. These are a great clue when it comes to the problems that are on this next page, because you can go step by step to actually figure these out. Okay, so on the problem on the next page, I gave you a sample problem, and then I asked you to actually go through and calculate this. The sample problem here, this is taking you from the very beginning where we have heating up some ice all the way to going to the gas phase again. Okay, so there's going to be three types of calculations involved in these types of problems. The first is our heat of fusion, our heat of vaporization, and then our specific heat. Think way back to chapter 4 or 5, where we did specific heat calculations, like Q equals MC delta T. You all remember talking about that? Very vaguely? That's going to be involved in here as well. So we have, if you think through this process, the heat of fusion, remember we have our phase diagram that looks kind of like this. This was where it was a solid, up here is a liquid, and up here is a gas. So we have this first part right here, that is a temperature change. That is going to be the Q equals MC delta T part. Then we have our heat of fusion up here, which is multiplying the moles by that HF, the heat of fusion. Right here we have heating our liquid. That's another Q equals MC delta T calculation. Here we're doing the heat of vaporization. So this is going to be that Q equals MH delta HV. And then once again over here, our gas, this is another Q equals MC delta T portion. So that kind of is our step-by-step for this calculation. So here we're told that we want to calculate the amount of heat required to completely convert 50 grams of ice at negative 10 degrees Celsius to steam at 120. So our first step is this Q equals MC delta T, where we have something going from a solid up to that 0 degrees, the melting point. For this, our Q is our 50 grams. Q equals, wow, that's our mass. Our mass is our 50 grams. C is at 2.09 joules per gram degrees Celsius. This is given to you. So this is something you would look up in a table. It is not something you have to have memorized. Then we have our temperature change is this right here. That's our delta T. And remember, delta T is always the final minus the initial, always. So you go through, plug in those numbers, and you get 1,045 joules. The next step is this step right here, where you have the conversion between the solid to the liquid. So here, this is at Q equals the M delta H of F. So this is our mass right here. And I gave you for this one, your delta H's were given to you in grams, so you didn't have to do any nasty conversions in the moles. Watch the units, they can change. So here we have 334 joules per gram. Once again, this is given to you. This is not something you have to memorize. You would just plug in the 50 grams, multiply it by that, and you're told that you have 16,700 joules. The next step is going this. So this is 1, this is 2, is this one right here. So now we're going from our liquid, and we're heating our liquid up from 0 degrees to 100 degrees. So we come down here. This is another Q equals MC delta T. We have our Q. This is, I'm doing it again, our mass, our C, and our delta T. So we have mass of 50. Our C is given to us at 4.18 joules per gram degree Celsius, and our delta T is 100 degrees Celsius. Plug all those in, you get 20,900. Down here, our next step, the fourth step, we have just breaking those bonds so we can go from a liquid to a gas. So fourth, we have our Q equals M times our delta H of vaporization. Heat of vaporization is 2,260 joules per gram. So I just plug those numbers in, and that gives me 113,000 joules. My last step then is to actually heat up my gas. So this is our step 5. So step 5, once again, is a Q equals MC delta T. And in this case, our specific heat is this 2.09 joules per gram degree Celsius again. That's our C, our mass is our 50, and our delta T is 20. That gives us 2,090 joules. Once you've done all of those steps, you then go through and add everything together. So you would add it all up. That is your final answer. So you have to break this apart into those 5 different steps. Then you can add it all together. None of these are tricky to do. It's a matter of remembering what to do when. So this phase diagram might help you visualize and just help you to break them up into the correct numbers of steps. Notice that the specific heat for heating up the solid versus the liquid versus the gas are different. So you can't just combine all those. People try that and it's wrong. You have to do all of those separately. Okay, questions on that? Okay, so I gave you guys the sample problem down here, and I asked you to calculate converting 429.1 grams of ice at -5 degrees Celsius to steam at 115 degrees Celsius. And it's just the same thing that we did. So we start off where we have our very first step is to get the solid from -5 degrees up to 0 degrees Celsius. So that is our Q equals MC delta T. So here our mass is just 429.1. My C I just pulled in from that number up above, and then our delta T is 5. That's what I get. My next step is actually doing the heat of fusion. So I have where I'm changing the bonds from the solid to the liquid. Mass, once again, is 429.1. My heat of fusion, I pulled down from that same example right here, is 334 joules per gram. The third step, I'm heating up my liquid now. So I'm going from 0 degrees all the way up to 100 degrees. So I heat that up. That's Q equals MC delta T. So I have my mass, I have my C, and I have my delta T. Fourth step, I'm going now where I'm making it from a liquid up to a gas. So I have my M delta H vap, that's my mass, that's my delta H vap. And then my last step is Q equals MC delta T again as I'm heating my gas up. So now I have my gas I'm heating up to 115 degrees Celsius. So my temperature change, I'm going from 100 degrees up to 115 degrees. So I have a 15 degree temperature change there. That's my C and that's my mass. I figure all those out, I add them all together, that's my final answer. So it's a multi-step process there.
Is it always in that order? The specific heat, then heat of fusion, then specific heat of vaporization, or does it depend on the substance?
Well, if it's starting below its freezing point, it's always in that order.
Okay.
I mean, and you can do those in any order really, as long as you add them up. And,
yeah.
it's gonna add up to be the same. I just do it in that order because it follows the diagram. That's what I always do.
For step number 3, that 100 degrees, where is that 100 degrees?
Because I'm going from 0 up to 100 degrees.
For the boiling.
Yeah.
Okay.
Yes. You multiply them together. Mass times the heat of fusion. And step number 2 is fusion, right? That was probably me typing it. I did this on Thursday when I wasn't feeling well. So yeah, that's probably a mistake. That's going to be larger than 763. Yeah. So let's scratch this part out. Sorry. I don't know what that equals. Okay, other questions on that? All right, like I said, the completed outlines, I think, were on, I put them on Blackboard, so you can go there and look at them as well and review them. Everyone clear what we're doing on Thursday? Yeah.
Are we still having a quiz on next Tuesday for acids and bases?
That's not Thursday, though. That's the next week.
Yeah.
Next Tuesday, yeah. That'll still go on.
Oh.
Yeah. All right, see y'all Thursday then. Please come and get any old papers. There's a stack. Some of you guys are really bad, like Larissa, Linda, and Natalia has some. Brian, both Brians I have. Cynthia I have. Old papers. Come next week.